Okay, I'm going to show you how to solve some kinematics word problems here. This is all going to be motion in one dimension with constant acceleration. I'd like to invite you right now to pause the video and copy out these 5 equations. There's actually 6 because I put that one as 1b. These are displacement is average velocity times the amount of time that it takes, which is really the definition of average velocity. Average velocity is displacement divided by time. Acceleration is the change in velocity divided by the amount of time that that change takes. Displacement is equal to your initial velocity times time plus half of your acceleration times time squared. Now, this equation may not be obvious, but I'll do a video later showing you the derivation of that from a graph of a position time graph, and then I'll also show you using calculus. It's much easier. This is the only equation that does not involve time. Your final velocity squared is equal to your initial velocity squared plus 2 times acceleration times displacement. So if you find yourself solving a problem where time is not in there and you're not looking for it, quite likely this is the one you're using. This equation here is really this one played out backwards. So whereas equation 3 has initial velocity, time, and an adjustment based on acceleration, this has final velocity and time and an adjustment based on acceleration. And then finally, I'd like to draw your attention here. Now remember, this only works if acceleration is constant. But if your acceleration is constant, then your average velocity is equal to your initial velocity plus your final velocity divided by 2. So with each of these problems, I'm going to give you the question, and then our first step is going to be identify, label all of the information that we have. So you might want to press pause, try this yourself. A bike increases its velocity from 10 kilometers per hour north to 20 kilometers per hour north in 6 seconds. What is its acceleration and what is its displacement? And that's during that time. What is its displacement during those 6 seconds? So what do we have? We've got time. The amount of time that this has taken is 6 seconds. We also have the initial velocity. It started out at 10 kilometers per hour north. So I'm going to write 10 kilometers per hour north. Now, both of these are north, but get used to stating that because sometimes that velocity is going to change, and when it does, that changes everything. So always state the direction along with your vector. Remember, your vector is any quantity that has both magnitude and direction. Our final velocity is 20 kilometers per hour. And that's north as well. Now, it's tempting to throw these numbers into these equations, but we must be careful. Because what you may notice here, velocity is measured in kilometers per hour, time is measured in seconds. So we're going to convert everything to our standard international units. Our standard unit for time is a second, so we're going to leave that. But our standard unit for distance is a meter, and time is a second, so our standard unit for velocity is meters per second. The conversion factor, if you have kilometers per hour, is you divide by 3.6. So for both of these, I'm going to divide by 3.6. And when you divide by 3.6, that will convert kilometers per hour to meters per second. The reason why that works is there are 1,000 meters in a kilometer, and there are 3,600 seconds in an hour. So if you take the number of seconds, 3,600, and divide it by the number of meters, 1,000, that gives you your conversion factor. And then you just might want to remember that the same velocity will be reported in a lower number in meters per second than it is in kilometers per hour. So that's how you can remember which one's dividing, which one's multiplying. So my 10 kilometers per hour is 2.78 meters per second. And that's north. So my 20 is going to be twice that. My 20 kilometers per hour is 5.56 meters per second north. Now, it's not okay to write 10 equals 2.78. However, with my unit stated there, it's perfectly all right to say that 10 kilometers per hour is equal to 2.78 meters per second, because those units adjust the number, making this equation work. Okay, so I've got delta t, that's the change in time, the initial velocity and the final velocity, and I'm looking for acceleration. So this one's simple enough. Acceleration is the final velocity minus the initial velocity divided by the amount of time that it takes. So I'm going to go ahead and just write out the formula first. Acceleration is the final velocity minus the initial velocity over the amount of time. So it is my final velocity, 5.56. Now, if everything's north, I'm just going to put north at the very end. 5.56 minus 2.78 divided by 6. And that's meters per second north. And I'm dividing by seconds. So I'm doing my units separately here. And this is going to be 5.56 minus 2.78. Remember, hit equals first. And then divide that by 6. And that's going to give me 0.46. So my acceleration is 0.46 meters per second squared. What is its displacement? So how far and in what direction did the bike travel in that time? Okay, I have a couple of choices here. I have the initial velocity, time, and acceleration. So I can use equation 3. Displacement is initial velocity times time plus half acceleration times squared. I also have final velocity. So I have final velocity, initial velocity, acceleration now, and time. So I could use equation 5. Displacement's final velocity times time minus half acceleration times squared. So either of those will work. However, I'm going to use this equation because it's easier. Displacement is my average velocity times time. And my average velocity is the initial plus the final velocity divided by 2. This one's going to be much easier to use. So my average velocity is my initial velocity plus my final velocity over 2. So it is 2.78 plus 5.56 divided by 2 meters per second north. .78 plus 5.56, and then I can divide all that by 2. It's 4.17. So that's 4.17 meters per second north. And now that I have that average velocity, and remember time, our time is 6 seconds. So our displacement is our average velocity times time. In this case, it is 4.17 meters per second north times 6 seconds. So it is 25.02 meters. See, the seconds cancel out and the direction stays the same. So we've traveled 25.02 meters north in that time. Okay, I'm going to do 3 more problems here. And I specifically chose these problems so that we could see a variety of the equations in use. So, problem number 2. A car was traveling west at 30 kilometers per hour when it slammed on its brakes, stopping in 2.5 seconds. How far did it travel while stopping? Okay, so what do we have here? We've got an initial velocity of 30 kilometers per hour west. Do we have a final velocity? We actually do. We don't see a number anywhere here for the final velocity, but we do hear that it stopped. It stopped in 2.5 seconds. So at the end of that time interval, its final velocity is 0. And the amount of time that took, delta t, is 2.5 seconds. Okay, we can't mix kilometers per hour with seconds. So we're going to divide by 3.6. 30 kilometers an hour is 8.3 meters per second west. So we have initial velocity, we have final velocity, we have time, and we want to know how far it traveled, so we're looking for displacement. Let's look at our list of equations here. We've got initial velocity, final velocity, sorry, I pointed backwards, initial velocity, final velocity, time. We can find acceleration. However, we can also find with initial and final velocity, and we're assuming we have constant acceleration for all of these, we can find the average velocity. And if we combine average velocity and time, we can find displacement. So we're going to do that. So the average velocity is the initial velocity, 8.3 meters per second west, plus the final velocity of 0, and that's divided by 2. Now I've seen people accidentally divide this by delta t. That's because these two equations look very similar. If you're not careful, at a glance, if you stand back, these two kind of look the same. We're adding and dividing by 2 to find the average. We're taking the difference and dividing by time to find the acceleration. So we want this one. The average velocity is 8.3 plus 0, so that's 8.3 divided by 2. So that's 4.17. So our average velocity is 4.17 meters per second west. And the amount of time was 2.5 seconds. Remember, displacement is average velocity times time. So it is 4.17 meters per second west multiplied by time, which is 2.5 seconds. $10.4. So our displacement is 10.4 meters. And we had a direction here, it's west. So our displacement is 10.4 meters west. Okay, this problem, we call this a freefall problem. A ball accelerates downward at 9.8 meters per second squared. And as you study physics further, you'll find that close to the Earth, if you can negate air resistance, all objects fall accelerating downward at 9.8 meters per second squared. If this ball is thrown upward at 13 meters per second, how long until it's 6 meters high? I initially put 16 meters high, and then I ran the numbers and realized it won't actually get that high, so change the question to 6. How long will it take for this ball to become 6 meters high? And what is its maximum height? So let's list all of the information that we have. A ball accelerates downward at 9.8 meters per second squared. It is thrown initially upward at 13 meters per second. Now, later on in your study of physics, you can use the concepts of kinetic energy and gravitational potential energy as a shortcut to solve this problem real quick. However, we're not there yet, so I'm going to do it using just the kinematics equations and the given information. So we have an initial velocity. Our initial velocity is 13 meters per second up. We must state the direction. We also have an acceleration, and our acceleration is 9.8 meters per second squared down. Now, 9.8 meters per second squared down is also negative 9.8 meters per second squared up. So I can call it either of those and it'll be correct here. How long until it's 6 meters high? So what I'm really looking for is what is the amount of time it takes for this to have a displacement of a positive 6 meters. How long will it take until it's 6 meters high? Okay. So I have initial velocity, I have acceleration, I have displacement, and how long, so I'm looking for time. So let's find an equation that involves those 4 variables. I've got initial velocity, acceleration, displacement, and I'm looking for time. I'm going to use equation 3. So my equation is displacement is initial velocity times time plus half acceleration times time squared. My displacement was 6 meters. My initial velocity was 13. My acceleration was negative 9.8. You see, here's how we make our decision. To write everything down in an equation and just use simple algebra to solve it, we need everything in the same direction. With one-dimensional motion, sometimes things will go in 2 different directions, but you can state them all as being in the same direction as long as you use a negative whenever something's going the other way. That's why in the equation, in my spot for acceleration, I'm going to put everything as up. My displacement is up, my initial velocity is up, and when I make my acceleration a negative, it's also upward. So everything here is up. Okay, so this looks like a little bit of a mess. We'll rearrange it to a familiar form. So half of 9.8 is 4.9. So I've got 6 is equal to 13 delta t minus 4.9 delta t squared. And I'm going to send everything to the left, and I'll just have a 0 on the right. So 4.9 delta t squared minus 13 delta t plus 6 is equal to 0. So how do I figure out how much time this was? We use the quadratic formula. And I'll write it out here in case you've forgotten it. it is negative b, where b is this coefficient here, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So remember, a is 4.9 in this equation, b is negative, and don't forget the negative, b is negative 13, and c is 6. If b is negative 13, negative b is going to be positive 13. So my time is 13 plus or minus the square root of 13 squared minus 4 times 4.9 times 6 all over 2 times 4.9. So I've got 13 squared minus 4 times 4.9 times 6 gives me a 51.4 under the square root sign. So when I take the square root, that is 7.17. So I've got 13 plus or minus 7.17 all divided by 2 times 4.9, which is 9.8. So I've got two answers. My answers are My answers are 2.06 or 0.59. Now, would it make sense for me to get two answers? And the answer is yes. Remember the question. A ball accelerates downward, but it was thrown upward. So if we look at the ball's motion over time, that ball started out here, it was thrown upward, but because it accelerated downward, it made its way up and then slowed down and made its way back down. So if I was to plot the position of this ball against time, and I was to ask when, at what time, was it at a height of 6, there would be two answers, because it hit a height of 6 on its way up, and then it hit a height of 6 again on its way down. So on its way up, after being in flight for 0.59 seconds, it was at a height of 6 meters. And then on its way back down, so that would be 0.59. And then on its way back down, it was at a height of 6 meters again after 2.06 seconds. So those are my two answers, and they're both correct. And you could write out a sentence saying that ball was at a height of 6 meters, 0.59 seconds after it was thrown. It was at that height on the way up. And 2.06 seconds after it was thrown, it was at that height again, but on its way back down. Second part of that question I asked was, what was the maximum height? What was this ball's maximum height? Okay, so how do I figure this out? I've got an initial velocity of 13 meters per second up. What's my final velocity? Well, as the ball makes its way up, so it starts out being thrown upward, it slows down, it stops at the top. So if I'm only interested in this part, as it travels up to its maximum height, I can say its final velocity is 0. Right now, you're maybe using a pen or a pencil to copy along as you watch this. Throw it into the air and watch it closely. As it gets to its apex, you will see that it stops momentarily right at the top. Now, the duration of the moment where it stops is actually 0, but it does, at its apex, at the top of its flight, hit a velocity of 0 before making its way back down. So, we've got an initial velocity of 13 meters per second, a final velocity of 0 because it stops at the top. We're looking for the maximum height. We've got an acceleration of negative 9.8 meters per second squared up. So I have initial velocity, I have final velocity, I have acceleration, and I am looking for displacement. So let's look at our list of equations here. And where do you see initial velocity, final velocity, acceleration, and displacement, and no time? It's this one right here. So the final velocity squared is the initial velocity squared plus 2 times acceleration times displacement. So my final velocity squared is 0. My initial velocity squared is 13 squared. My acceleration is negative 9.8, and I have an unknown displacement. Okay, so I hope I didn't rush through that algebra too quick. I'll recap it for you. So we've got 13 squared plus 2 times negative 9.8 times displacement. So I subtracted 13 squared from both sides, so I ended up with a negative 13 squared over here. And I multiplied negative 9.8 times 2, giving me a negative 19.6 there. I then divided both sides by negative 19.6, giving me a displacement of 13 squared over 19.6. Those negatives cancel out. So I've got 13 squared divided by 19.6, and that gives me 8.6. So my displacement is 8.6 meters. That's the maximum height that this object has reached. And I'll put in direction. It was upward.